probability, complements, and conditional probability. First, the basic concept was discussed. A few very interesting and important parts is that we should know that the probability is always between 0 and 1, and the sum is always 1. Complementary event was defined as probability of a complement equals 1 minus P of A. Odds against an event A is defined as P of A naught over P of A. And the actual odds in favor of event A is the reciprocal of that, which gives rise to the definition of a payoff odds and the net profit. Net profit is defined as payoff odds against event A times the amount of bet. Addition and multiplication property was discussed. Probability of A union B equals probability of A plus the probability of B minus the probability of A intersection B. The reason being is because probability of A intersection B is accounted for 2 times, once for calculation of P of A and once for calculation of P of B. And if there's anything in common, it has to come out unless they are mutually exclusive. Definition simply means the probability of A intersection B is equal to 0 if they are disjoint or mutually exclusive. Then how do we calculate probability of A intersection B? It depends whether they are independent or dependent. If they are independent, their product will do the job. If they are dependent, the product of P of A times the probability of conditional probability B given A. As for complementary events, they add up to 100%. They have nothing in common. So P of A plus P of A naught adds up to 1. So with that, we discussed the probability of at least 1. And it is easier to calculate probability of none and subtract it from 1. We had this example. We were interested in finding the probability of at least 1 girl. So you can calculate the none probability of all boys subtracted from 1 or 100%. 3% of ties sold in the United States happen to be bow ties. So if 4 people are chosen randomly, what is the probability of at least 1 purchasing the bow tie? We notice the probability of purchasing the bow tie, P of B, is given as 3% or 0.03. So its complementary event becomes 1 minus that, which is 97%. In the case of n equals 4, if none of them buy it, it has to be the product of 0.97 by itself 4 times, and then 1 minus that would be the answer. I believe this is the last one we did. And so we are going to move on from here.
If 6% of damaged iPads are damaged by backpacks, if 20 damaged iPads are randomly selected, find the probability of getting at least 1 that was damaged in a backpack. Is the probability high enough so that we can be reasonably sure of getting at least 1 iPad damaged in the backpack?
Probability of D for damage is given as 6%, N equals 20, and probability of not being damaged can be calculated as 1 minus that. So in essence, when P of D is given, we can quickly see P of D naught. Now we have how many of them? We have 20 of them, and we are going to treat them as independent. Therefore, in this case, for the probability of no damage backpack, we have to raise this to the power of n, whatever n may be. If you have 5 of them to the power of 5, 10 of them to the power of 10, and 20 of them to the power of 20, which is simply 0.94, remember 1 minus 0.06, 0.94 to the power of 20, and the answer is 0.2901. And again, I really can't emphasize the importance of carrying enough decimals. So you want to carry as much as possible. If, however, you're answering the question for your homework, you want to do it accordingly. Now, P of at least One damage would be 1 minus the probability of none. Probability of at least one damaged is the same as 1 minus the probability of none. And so the answer is about 71% roughly. 0.7099 at 71% rough. And so what's going on here? Let's look at the interpretation of that. When n is 20, okay, probability of getting at least one iPad damage in a backpack is 0.7099. This probability is not very high, so to be reasonably sure of getting at least one iPad damaged in a backpack, you need to get more than 20. So n equals 20 is not enough. To make sure we understand what's going on here, very high probability means as n, namely the sample size, gets larger, the probability gets closer and closer to 1. That's the idea behind this. Let's discuss conditional probability.
A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. Notation. P of B given A denotes the conditional probability of event B occurring given that event A has already occurred. It can be found by assuming that event A has occurred and then calculating the probability that event B will occur.
So here's the formulas. Probability of A given B is defined as probability of A intersection B over the probability of B. Probability of B given A is the probability of A intersection B divided by P of A. Needless to say, the denominator can't be 0. It's the same formula in essence. Now, this is the one that gives rise to the following definition. Probability of A intersection B. Now this, we can use the product rule, cross product I mean. Probability of A given B times the probability of B. Now if we do cross product for this one, we get probability of B given A times the probability of A. If A and B are considered independent, if A and B are independent, then conditional probability becomes a marginal probability. What do I mean by that? If A and B are independent, probability of A given B is equal to probability of A. And this is what I want you to pay attention to. Remember when we defined independency, we said A and B are independent if the occurrence of A has no effect on the occurrence of B. What does it mean? This definition that I'm writing using numbers and equality and math makes a perfect sense. This is what it means. So if you want to prove independency, the definition is fine and dandy, but understand how to prove it with math. And also, the following must be true. Probability of a B given A is equal to probability of B. In both cases, conditional probability becomes a marginal probability. When I say marginal probability, that means P of A, a simple event. If you will, probability of A given B is the same as probability of A. Probability of B given A is the probability of B. Now, if you want to prove independency, one of them is good enough. You don't have to prove both of them. In which case, this simply becomes the probability of A times the probability of B. If the two are independent, that's what happens. Let's go to the next example.
The probability that Sean parks in a no parking zone and gets a parking ticket is 0.08%, or 0.08. And the probability that Sean cannot find a legal parking space and has to park in the no parking zone is 0.40. If Sean arrives at school and has to park in a no parking zone, find the probability that he will get a parking ticket.
I like to start with letters, in this case N. We're going to let N represent parking in a no parking zone and T getting a ticket. So that makes life easier when we want to do the math. So let's see again what is given. Those N and T, it is your choice. You pick up anything you want, a variable to make life easier, unless it's given to you. Normally, the initials would make it a good choice. With that being the case, let's see what is given. So the very first number I see is number 0.08. And it says the probability that Sean parks in a no parking zone. And we can write that one as probability of N intersection T as 0.08. And then Sean cannot find a legal parking and has to park in a no, so it's 0.4. Probability of N, no parking zone. So those are the given. With that being the case, let us write one of the conditional probabilities, probability of A given B or B given A. If we write probability of T given N, this is how we write it, just for the sake of argument. If we were to write probability of N given T, the numerator would be the same, but the denominator would be P of T. Let me write that, and I'll tell you why we are not going to use that. It's important to see why we are not using that. Probability of N given T is the probability of, whether you write N intersection T, purpose I'm going to write T intersection N. It makes no difference. T intersection N, N intersection T, the same thing. But now, because N given T, pay attention to the given. Even when you want to calculate it when the numbers are simply there, start with the given as the denominator, because what it does, it shrinks your original sample space. So let's call this number 1, let's call this number 2. And you can write both of them and then see and figure out which one you need. As you can see, we have the numerator fine, but as far as the denominator, we only have P of N. Therefore, we use the first one instead of the second one, and we just plug in everybody. And of course, we were interested in finding that specific conditional probability, probability of T given N, T given N, a conditional probability.
Group of 150 randomly selected CEOs was tested for personality type. The following table gives the results of this survey. Contingency table or frequency distribution table for bivariate data. A, if one CEO is selected at random from this group, find the probability that this CEO has a type A personality, is a woman, is a man, given that he has a type A personality, has a type B personality, given that she is a woman, has type A personality, and is a woman.
Contingency table or frequency distribution table, that means the same thing. Bivariate data, then we are talking about different types of data, as you can see. Not only we are looking at gender, we are also looking at personality. That's why there are two pieces of data that are being, types of data, if you will, are being discussed. So, number one, the question that is given here is very straightforward because the table is given. Now, what if you're not given a table? They may give you numbers and you got to fill up the table accordingly. And it happens often. So it's very important that you be able to come up with the table on your own if the numbers are there. First, let's discuss the table so we understand what's going on. So what's happening is that when we look at rows, men, just reading it, men, type A, 78 of them, type B, 42 of them, and we have a total of 120. Women, we have 19 type A, 11 type B, total of 30. And that gives us total of 150 CEOs. But if you look at type A column, we have 78 of them men, 19 of them women, total of 97. Type B, 42 men, 11 women, total of 53. So understanding the table. Now, it is important to look at the very first and the second and notice it's a marginal probability. It's a simple probability. What is the probability for the first one? Notice what I did. I put A for type A, B for type B, M for men, W for women. So to make life easier when we do probability. So the first one is asking for probability of A, which is simply N of A over N of S. Your N of S Originally, your sample space contains of everybody 150. For any marginal or simple probability, your sample space contains 150 elements, subjects, objects, however you want to put that. Therefore, N of A is simply 97. We have 97 of them. You can look at the total, or if the total is not given, you can say 78 plus 19 divided by 150. Now, if you left it as that is absolutely fine. If it's a fraction, the only thing, remember, you want to put it in lowest term. If it can't be done, you're done. If you insist to go to decimals, you're really. The next one is also a marginal or simple probability. It's asking what is the probability that the person that we select is a woman. So probability of W is N of W over N of S. And if you have the total, as we have here, it is simply 30 over 150. But if we didn't have it, then we would add 19 and 11. Okay, that's why I want you to see how it's done in case, because the total many times is not given. And so because we can simplify, we must. Your sample space of 150 is no longer there. It is shrunk. By how much? Is a man given that he has type A personality? So first let's write it properly. We want the probability of M given A, which is the probability of M intersection A over the probability of A. Now, what I want you to notice, and I'm going to write this at top of it, this one is the same as the numerator, is N of M intersection A over N of S. This is the numerator. The denominator is N of A over N of S. I want you to see this is the way it works. And now you're dealing with a complex fraction. You can drop the N of S. So it becomes N of M intersection A over N of A. So it becomes, anytime you're dealing with a conditional probability, I highly recommend you start with the denominator. So right away after the given sign, you see A. So how many have A personalities? That is our new sample space. The sample is original sample space of 150 is no longer there. It has shrunk to 97. So in my opinion, to make life easy for a case like that, start with the denominator. Start with your sample space. The new sample space is no longer there. So it's 97. Now, out of those 97, we want men intersection with A. So the column is type A, the row is men, put them together, what's in common? That would give you 78. I explained that because if you honestly follow this thing, then anytime you come up with the conditional probability, you have an easy time. Conditional probability, your sample space is no longer there, it becomes smaller. And it becomes a new sample space. What it becomes is after the given. Here's another example. Type B personality given that she's a woman. So now your sample space is no longer 150 again, but what is it? Is the sample space that contains all women. Right after given, that is your new sample space. And so the denominator is 30. So you want to start with the denominator. So with that being the case, now you look at the B personality, the column that has type B and the column that has women, and you put them together, and the common number is 11 out of 30. So you're looking at this column and this row, putting them together, and you see number 11 is in common. Now, anytime you have a given, your sample space is no longer there, but anything other than that, your sample space goes back to the original 150. So when we are looking at the next one, it says has type A personality and is a woman, your denominator remains at 150. It's important to know that it is always the total size of 150 with the exception of conditional probability. The moment you see given, it is no longer there. So with that being the case, you want the probability of A intersection W. By definition, is N of A intersection W over N of S, we start with the sample space always. In this case, is the whole thing, 150. And what is in common between the A column and the W row? And that's 19. Now, you can just read it from the table, and that's good enough. I just wanted you to see the formula that I discussed in the previous page with the cross product. We could write it in the following manner. Probability of A times the probability of W given A. Or probability of W times the probability of A given W. I highly recommend you spend some time getting comfortable with this and how we arrived at it, because this will help you understand conditional probability. And of course, you see that in this case, 97 and 97 cancel each other. We get the same 19 over 50. In this case, 30 and 30 cancel each other, and we get to the same answer, 19 over 50. Do you have to do it this way? Absolutely not. But I want you to understand, if need be, what happens when it comes to finding the probability of an intersection where A and B, or in this case, it's A and W, are dependent. They are not independent. We are repeating the same question, everything is there. We're just adding a couple more questions. Okay, the next one is asking, if one CEO is selected at random from this group, find the probability that this CEO is a man or has a type B personality. And we use the union of events. So we want the probability of M or B, probability of M or B. That's what we are using. So it's probability of M plus the probability of B minus the probability of M intersection B. And remember, we normally use the notation U here. It looks like a U, okay? It's not a U plus. It's a union of events, and it looks like an M. So that's equal to probability of M plus probability of B minus probability of M and B. Understand that it is not a conditional probability, in which case the sample space is 150. So one easy way to write it is as follows. N of M plus N of B minus N of M intersection B over N of S. The denominator remains at 150. And so what happens to the numerator is very simple. All we have to do, just put the numbers in. So we look for the M row, 120 total. N of B, we look for the B column, 53 total. And between the two, 42 is in common, which means it has been accounted for 2 times. That's why we subtract it and we get to the answer. There is a different method to find probability of M and B. You recall we had the probability of A personality and women A and W in the previous page. So I want to show you that one also. And by no means you have to go that route. I just want you to be exposed to that in case. So this is the way that M intersection B is calculated. So you can say with the probability rather than N dealing with P, you can say probability of M. So I'm looking at this formula now. Probability of M, 120 over 150, plus probability of B, 53 over 150, minus probability of M and B. We wrote that 2 different ways, like 120 over 150 times 42 over 120, so they cancel each other. Or if we write it in this fashion, they cancel each other. And all of them give us the same answer. You don't have to do it that way. I want to make sure you understand the process in case you come across it. So the process is what matters here. The next thing is, are the events W, women, and type A, just A, mutually exclusive? Are the events type A and type B mutually exclusive? In each case, we go with the definition. Mutually exclusive means what? Calculate the probability of their intersection. If it's 0 mutually exclusive, it's not. they're not. So for example, when you look at the probability of A intersection W, A intersection W, you know it's 19 over 150. Because this number is not zero, they are not mutually exclusive. On the other hand, A and B, they have nothing in common. Because this probability is zero, the answer is yes. You don't have to explain and write a whole paragraph. All you have to do, calculate, use math. The next part is asking for independency. Are the events type A and men independent? Again, we don't want to write a whole paragraph explaining what we believe and so forth, because that really may not be good enough. So why don't we show that mathematically, and that would be a good proof. And what is that? We looked at this idea of independency, that a conditional probability becomes a marginal probability if they're independent or it doesn't. So because we are looking at A personality versus men, we can look at probability of A and probability of A given M, or we can look at the probability of M and probability of M given A. They must be identical if they are independent. And those are easy to calculate. We've done that. We've dealt with the conditional probability already. So probability of A is 97 over 150. Probability of A given M, remember now M, the total size for M becomes a new sample space, 120. How many of them are A personality? 78. Because these two numbers are not identical, you don't even have to simplify the right side to realize they are not. If you don't realize them, you can do the cross. Remember, to show two fractions are equal, their cross product is equal, or you can write the decimal notation for each. They are not equal. So that is the proof. You don't have to do the next one, but I want you to see the next one, either this one or this one. You know probability of M is 120 over 150, and M given A is 78 over 120. I want to make sure everybody understands why. M given A is M given A. Okay, this is wrong. So let's actually do this together, since this is wrong. I'm going to start with the denominator. Remember what I told you? I said, the moment you see a conditional probability, it means your sample space, original sample space, in this case 150, is no longer there. So what is your new sample space? What comes after given A? So how many A personalities?
97.
97. Now, out of those 97 total, how many are men?
78.
And so the answer is 78 over 97 and not 78 over 120. And again, the two are not the same. You don't have to. Okay, let me give them numbers. Number one, number two. You don't have to use both. One is good enough to prove that, everybody. As I mentioned, I want to show you both so you can see how we arrive at the answer. So this is the proof that they are not independent. Type A personality and men, those events are not independent. Okay, that's a proof. We're going to move on to the next example.
If one of the 555 test subjects is randomly selected, find the probability that the subject had a positive test result, given that the subject actually uses drugs. That is, find the probability positive test result given subject uses drugs. B, if one of the 555 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. That is, find the probability subject uses drugs given positive test result.
So we are given the table. And again, to make life easy, we are using D to represent subject using drugs, N, D not using it, and then P for positive and for negative, just to make life easier. And of course, the table has everything, including the total row and total column. So we have all of them. So when we look at the first one, the probability of P given D, by definition, is the probability of a P intersection D over the probability of D. So notice your sample space originally contains 555 subjects. With the conditional probability, it is no longer there. It goes down. So I want you to see why we start with the denominator. So if we were to do it with the denominator in the manner of dealing with n of the top over n of the bottom, as I showed you last time in the last example, why it happens that. So D has a total of 50. So the denominator is no longer 555, but rather only 50. And subject uses drugs. How many of those 50? I'm looking at the very first row, if you will. Subject uses drugs, D. So there's a total of 50. And therefore, how many use the drugs is 45, 45 over 50. Or you can say 45 over 555 over 50 over 555. That is the probability, and it changes to 9 over 10 or 0.9. So what does it mean? Here's a very interesting interpretation. A subject who uses drugs has a 0.9 or 90% probability of getting a positive test result. So as you know, none of the tests are 100% correct. So it shows 90%. Now, if we are using the conditional probability for D given P, the numerator stays the same, but the denominator now is probability of what comes after given. There were 555 subjects. They are no longer there. So we are going down to what comes after the given. So after the given is P or positive. So that means you're dealing with the column of positive, total of 70 sample size. It shrinks and it ends up being with number 70, which is the first column positive test. Why is that? Because it says given positive test. And out of those, how many in that column use drugs? 45. You can write them as probability or just don't write 45 over 70 and simplify it, and it becomes 9 over 14, and it becomes 0.643. Again, the purpose of this question was to make sure we can calculate conditional probabilities and we don't confuse this. Again, pay attention to A versus B. Probability of positive test result given subject uses drugs versus probability of subject uses drugs given positive test. And the interpretation in this case is that a subject who gets a positive test result, there is a 64.3% or 0.643 probability that subject actually uses drugs. And note, it's extremely important. The two are not the same. I really can't emphasize this enough with me. These two are not the same. So we don't want to confuse them. And that's why I think you really want to pay attention to this question later on, go over it again, make sure it makes a perfect sense to you. Confusion of the inverse in general. Probability of B given A is not the same as probability of A given B. There may be some cases that they become equal. Okay, we are not interested in that, but it is important to know that they are not the same. Let's look at this example. Consider these events. D represents it is dark outdoors, and M represents it is midnight. So let's look at the conditional probability of D given M and M given D as an example and see how that works. Take a look at this explanation. We are ignoring inconsistencies. So probability of a D given M. In other words, the question is, what is the probability that it is dark when it's midnight? Normally is 1 or 100%. Probability of M given D is probably 0 because the probability that it is exactly midnight given that it is dark is almost 0 or maybe close to 0, by the way. Confusion of the inverse occurs when we switch those probability values or think that they are equal. The next topic of probability includes counting. Again, the basic concept, probability is between 0 and 1. The sum is always 1. Complementary event, they add up to 1. Odds against, odds for. Probability of A union B is probability of A plus probability of B minus the probability of A intersection B. And if the two events are independent, the probability of A intersection B is simply their product. If they are not, then the probability of A intersection B is the probability of A times the probability of B given A. So that's important to pay attention. We discussed the at least concept. Probability of at least is 1 minus the probability of none. And the reason we use that because a lot of times calculating the probability of none is very simple. So we can go that route. Then we discussed the conditional probability versus marginal probability. So probability of A given B or B given A, the notation, what it means, and how it's calculated. By definition, probability of A given B is the probability of A intersection B over the probability of B, and the probability of B given A has the same numerator, but a different denominator. Probability of A intersection B over the probability of A, needless to say, the denominators cannot be negative. In this case, dealing with the counting, we require much greater use of formulas as we consider 5 different methods for counting the number of possible outcomes in a variety of situations. And not all counting problems can be solved with these 5 methods, but they do provide a strong foundation for the most common real applications, and that's what we are going to look at.
For a sequence of events in which the first event can occur n1 ways, the second event can occur n2 ways, the third event can occur n3 ways, and so on. The total number of outcomes is n1 times n2, etc. For a sequence of 2 events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways.
So that is known as the fundamental counting rule or multiplication counting.
Factorial rule. The number of different arrangement order matters of n different items when all n of them are selected is n factorial. The factorial symbol denotes the product of decreasing positive whole numbers. By special definition, 0 factorial is equal to 1. The factorial rule is based on the principle that the first item may be selected n different ways, the second item may be selected n minus 1 ways, and so on. This rule is really the multiplication counting rule modified for the elimination of one item of each selection, on each selection.
So that's the synopsis of what's coming up. Let's start with a simple example.
A paint manufacturer is making different paint categories as follows: color, red, blue, white, black, green, brown, yellow; type, latex or oil; texture, flat, semi-gloss, high gloss; use, outdoor or indoor. How many different kinds of paint can we make if we can select one color, one type, one texture, and one use?
Okay, so this is the basic multiplication rule or the fundamental counting rule. So simply put, we just see the product. The product of what? How many colors do we have? How many types do we have? How many textures do we have? How many uses do we get out of it? And we replace the numbers that are given. And so we see that we have 7 different colors. Then the type, we have 2 different types. Textures, 3 different types. Use, 2 different types. And plug in. So this is a simple case dealing with the fundamental counting rule.
When making random guesses for an unknown 4-digit passcode, each digit can be 0, 1, ... 9. What is the total number of different possible passcodes? And given that all of the guesses have the same chance of being correct, what is the probability of guessing the correct passcode on the first attempt?
First, it is important to know that when we go from 0 to 9, that means we have 10 digits. We want a 4-digit passcode. So basically we have 4 spots. In each case, since there is no restriction, we can use 10 digits in each case. There are 4 of them, 10 to the power of 4. If there are 5 of them, 10 to the power of 5, and so on. So 1, 2, 3, 4 different spots. So it's the simple case of multiplication rule or the fundamental counting rule. 10 to the power of 4. Everybody has the same chance of being correct. So it's just simply 1 out of 10,000. Enough C standing for being correct. N of S standing for the sample space or sample size, 1 over 10,000. All right, counting.
Multiplication counting rule, the fundamental counting rule. For a sequence of events in which the first event can occur n1 ways, the second event can occur n2 ways, the third event can occur n3 ways, and so on. The total number of outcomes is n1 times n2 times n3, etc. For a sequence of two events in which the first event can occur m ways and the second event can occur n ways, the events together can occur a total of m times n ways. And 2 factorial is the product of all positive numbers from 1 to a number.
We already discussed the multiplication or the fundamental counting rule. N factorial, it simply starts with n and it goes down all the way to number 1. We multiply those numbers. So if we said 10 factorial, that means 10 times 9 times 8 all the way to 1. 1 factorial and 0 factorial are 1. Actually, 0 factorial becomes 1 because of the definition of a combination.
Permutation is an arrangement of objects in a specific order. Order matters. The letter arrangements of ABC, ACB, BAC, BCA, CAB, and CBA are all counted separately as 6 different permutations. When n different items are available and r of them are selected without replacement, the number of different permutations when order counts is given by
NPR is n factorial over n minus r factorial. N factorial, you can go all the way down to r items and then times r items and get rid of it. But what I want to mention is different notations. By the way, NPR, this is the way you write it if you want to use a TI. And what it means is you put the number first, then you look for NPR, and then you put the R first. I will show you in a moment as far as how you use a calculator if need be, but conceptually is really not difficult. Now, NPR, we can write it as P and then NR. In case you see that, that has the same meaning. That means permutation of n objects when we choose R of M only. And R is always less than or equal to n. Can it be equal to n? Yes. Can it be larger than n? Absolutely not. And basically, you're dealing with different objects, and order is important. And a simple example that ABC, for example, is not the same as ACB. It's very simple. Think about a code, a password that you want to use. Even if we want to go with something as simple, then all we have to do, change the order, and it's a new password. Order is important.
When some items are identical to others, the number of different permutations, order counts, when n items are available and all n of them are selected without replacement, but some of the items are identical to others, is found as follows. N1 are alike, N2 are alike, and Nk are alike.
In the third case, we are dealing with different items. But what happens when some of them repeat? Now the formula changes. The permutation rule changes to n factorial over n1 factorial times n2 factorial all the way to n sub k. And finally, combination.
Combination is a grouping objects. Order does not matter. When n different items are available, but only r of them are selected without replacement, the number of different combinations, order does not matter, is found as follows.
Pay attention to the difference between 3 and 5. In the case of a 3, A, B, C, and ACB, and so on and so forth are different. But number 5 says it doesn't matter. ABC is the same as ACB. So when would that be? There are cases that you may want to choose, let's say, a committee of 3 students, let's say, from the class. Then order is not important. You want 3 students. So that becomes a combination, and it is up to you to recognize that. However, if we said instead of just committee of 3 students, we said we want a committee of 3 students such that the first one is the president of that committee, and the second one is vice president, and the third one is the treasurer, and so forth. Now, order makes a difference. So you have to pay attention to the question and see what happens to the order. Now, in this case, basically, the answer is n factorial over n minus r factorial times r factorial. What I want you to pay attention to is the notations. We have 3 different ways. If you put it as a parentheses, in essence like a pair, that means a combination. Or CNR or NCR, that works the same way.
We ought to travel to visit the presidents, all from different age groups of 5 different companies. How many different travel itineraries are possible? If the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest?
All from different age group. How many different travel itineraries are possible? There are a couple of different ways to approach this. So let's look at various approaches. One is simply n factorial. The other one is that may make it a little bit easier to understand. We have 5 spots to fill. So we put the numbers that we have. First and foremost, we have 5. So we are multiplying those. Now the next one, we no longer have 5. One of them is gone, 4. And then we go down in the same manner. And so you can go with the simple multiplication rule. So we can use n factorial, or we can use the multiplication rule, or we can see that it's a permutation. If you look at the top, I'm showing you here how to use a calculator to get to a factorial. In order for you to come up with the answer for a factorial, you have a choice. Calculate it by hand. Well, 5 times, so you use a calculator. But if it's a larger number, it's easier just to use a calculator. So what do? First, you put the number n, then you press math, then select probability, then select factorial, and enter. If you want to use permutation or combination, you start the same way. You start with entering n, you press math, you select PRB or probability, and then you select NPR or NCR, depending upon what you need, and then you enter the value of R. Finally, for this question, if the itinerary is randomly selected, what is the probability that the presidents are visited in order from youngest to oldest? There's only one way to have the proper order, and it's only 1 over the total size n of s, which is 1 out of 120. I want to quickly show you how to use a calculator. If we want to use a factorial, in this case 5 factorial, then we press math, we go to the right, and then we bring it down to the factorial. We press enter, it shows 5 factorial, and it is 120. Using permutation, the same thing again, 5, and then math, going back to PRB, going down to NPR, and we're going to choose 5, and it gives us 120 again. So this is how you would use the calculator to speed up the process. Here's the next example.
Business owner has a choice of 5 locations in which to establish the business. She decides to rank each location according to certain criteria, such as price of the store and parking facilities. A, how many different ways can she rank the 5 locations? B, if she wishes to rank only the top 3 of the 5 locations, how many different ways can she rank them?
This is practically the same as the previous example. And so, again, you can use the fundamental multiplication principle. We have 5 locations. Those are the choices. So you establish just 5 spots and you multiply, which means the first, the second, and so forth. So we have those, and that gives us 120, or you can use a factorial. Either way is fine. You can use a factorial in the same manner, or the permutation, and no matter what, all of them will result in the same thing. So multiplication principle, using a factorial, or permutation, it's the same thing. The second one, we only want 3 of it. So again, we have a choice. We can say, okay, we want 3 of it. And so we go 5, 4, 3, and that's it. Or you can use permutation, 5, choose 3. Sometimes this notation is used. Both of them mean the same thing. End up giving us number 60 as the answer. So we want to choose 3 out of 5.
TV shows 7 ads to use on a program. If we select 1 for the opening, 1 for the middle, and 1 for the ending of the show, how many different ways are possible?
The very first thing is to answer this question, does order matter? You have to realize order is important simply because of the way they have told us. One for the opening, one for the middle, and one for the ending. So where do we use that makes a difference? Do we use a specific ad for the opening or for the ending or for somewhere in the middle? Okay, so where do we use that? So that's why order is important. So you've got to ask yourself, order is important or not? And you have 7, you want to choose 3 from. So your N is 7, your R is 3, but is it permutation or combination? That's what you want to answer. So it's simply a permutation, 7 factorial over 4 factorial, 7 minus 3 or 4 factorial. What I want to show you is this. Obviously, you can use a calculator, it's fine and then. But if you were to simplify it by hand, how would you do that? A fast and easy way is very simple, is as follows. You look at the smaller of the two. The smaller of the two is the 4 factorial, so you keep it intact. Number 7 means multiply 7 all the way to 1. Number 4 means multiply 4 all the way to 1. So wherever you stop, you can change it to a factorial. For example, you can say 7 times 6 factorial, but it doesn't help us. Instead, we got to go 7, 6, 5 times 4 factorial. Why do we do that? Because we have the same thing down here. They can cancel each other. It's a simple way of approaching that. 7 times 6 times 5 is the answer. Or you can go with the simple multiplication principle. The first one, okay, we have 7 choices. So for opening, for example, I'm going to put O. For opening, we have 7 choices. Then for M, for the middle, since 7 is gone, one of them is already gone, we have only 7 minus 1 or 6 choices. And for the ending, then we have only 5 more left. So their product is the answer. So either way, it will do the job.
A department musical director will select 2 musical plays to present in a year, one in the fall and one in the spring. There are 9 to pick from. How many different possibilities are there?
We are using 2 musical plays, one in fall and one in spring. That means order matters. So you go with the permutation, and P9, 2 means 9 factorial divided by 9 minus 2 factorial. That's how we get 9 factorial over 7 factorial. So the top can be simply 9 times 8 times 7 factorial. They cancel each other and the answer is 9 times 8. Or you can say there are 2 spots. For the first spot in fall, we have 9 to choose from. The second one for spring, we have 8 left, and we use the fundamental principle of multiplication. And we end up with the same answer, 9 times 8 equals 72.
An editor has 8 books to review, and he can only use 3 reviews in his paper. How many different ways can the 3 reviews be selected?
The question we should ask is very simple. What about the order? Does order matter here?
No.
No.
No, and that's it. Extremely important that you read the question and decide whether order is important or not and why. We are looking at 8 books and we're just going to choose 3 of them, and that's all that matters. Order is not important. Therefore, you use a combination. And so this is another way of writing combination, format, any of them is fine. And so combination of 8, choose 3, that's the most important. This is n factorial, which is 8 factorial, over r factorial, which is 3 factorial, times n minus r factorial. By the way, whether you put the r factorial first or n minus r factorial first, it makes no difference. Now, again, I want to show you how you can simplify it by hand if need be. The largest number is 8, and the next largest number is 5. So in the denominator, you keep the 5 factorial. In the numerator, you can write 8 factorial as 8 times 7 times 6 times 5 factorial. And the 3 factorial in the denominator must be written as 3 times 2 times 1. And so we can get rid of the largest factor between the top and the bottom, which is 5 factorial. Number 6 and 3 times 2 are identical. So you're left with 8 times 7 over 1. And that's your answer. Just in case, you can write the permutation divided by r factorial. It's the same calculation. You don't have to worry about that at all. I'm mentioning it just because of the relationship between the combination and permutation. You don't have to worry about that at all. When you compare the formula for permutation versus combination, you see that if you divide the permutation by r factorial, it gives you the combination formula. Okay, I just wanted you to notice that, that's all. We're going to look at the next example.
In a club, there are 7 women and 5 men. How many different possibilities are there? A committee of 5 persons is to be chosen as follows. A, 3 women and 2 men. B, 2 women and 3 men. And then C, 5 persons.
So let's see how this thing works. The way this is telling us is that we are interested in a committee, and the restriction, for example, for part is that you want 3 women and 2 men, and order is not important, because that's the first thing you should ask yourself. Is order important? No. Okay, we just want 3 women in any order, we want 2 men in any order. So it is really a combination of 2 rules, a combination and fundamental multiplication principle. Women and men. How many women? How many men? The way we come up with the women is a combination of 7 choose 3. Same thing for men. Combination. Combination of what? 5 choose 2. So now the fundamental principle of counting says multiply these 2 numbers. So all we have to do, find each case, multiply by each other. And that's what we are going to do. So we are going to find those and calculate them and multiply. So with that being the case, the first one is 7 factorial over 3 factorial, r factorial, okay, times 4 factorial. The next one is 5 factorial over 2 factorial times 3 factorial. And so 35 possibilities for women and 10 for men. And we end up with the product of 350 as the answer. Now we are looking at a slightly different type. In this case, we want the other way around. We want 2 women. So we have to choose combination for women would be C 7 2, and we want 3 men, C 5 3. And we do exactly the same thing. We calculate each piece using the combination formula. The first one is 7 factorial over 2 factorial times 5 factorial. And for men would be 5 factorial over 3 factorial times 2 factorial. And we simplify. We multiply them, and we end up with 210. By the way, one way to do that, you can say for this one, 7 factorial, 2 factorial, 5 factorial. Then this is 5 factorial, 3 factorial, 2 factorial. So if you write it in this manner, you can drop the 5 factorial. Now, by the way, 2 factorial is 2 class, and 3 factorial by now you know is 6, or you just write down 3 times 2 times 1 and then do the math. This is another way of doing it. Again, simply dealing with fractions. Finally, it is asking for 5 people, which means there is no restriction. So in that case, again, it's a combination, but it's a combination of total. Total is adding these 2 numbers. We have total of 12 people, and we want to choose 5 of them. And order is not important, and it simply becomes combination of 12 choose 5, which is 12 factorial, over 5 factorial times 7 factorial. When you go through the process and simplify, you get 792. The denominator is 5, 4, 3, 2, 1, and I keep the 7 factorial. And so the top is 12 times 11, 10, 9, 8, 7 factorial, and they cancel each other. And then you can simplify things. For example, you can drop the 12 and 4 times 3 and take it from there. Maybe, for example, 2 and 5 can be dropped. 2 and 5 with 10 and take it from there. That would be the fastest way to do the simplification of the fraction and putting it in lowest. So here's the next one.
A store has 6 TV graphic magazines and 8 news time magazines on the counter. If 2 customers purchased a magazine, find the probability that one of each magazine was purchased.
Let's see how we do that. First, let's write it in a manner that it's easy to follow. TV graphic, we want to choose one of the 6 magazines. News time, we want to choose one of the 8 magazines. And therefore, we have a total of 2 to choose from, a total of 14 magazines. And so what we want is to find the probability that one of each magazine was purchased, and it's a combination in the following manner. The probability is defined as the number of outcomes for the event of interest over the sample size. First, I want to discuss the sample size, the total possible outcome. I want to discuss the sample size. Is combination of 14, choose 2. That would be your sample space as far as the size is concerned. The first one, really, you have 6 outcomes. The second one, you have 8 outcomes, meaning to get the first one is C, combination of 6, choose 1. And by the way, it becomes 6. And the other one is the combination of 8, choose 1. And it becomes 8. And while we are at it, let me just give you this CN1 is N when you calculate it. So whatever, when you're choosing one out of it, okay? Whatever the number N is, that would be the answer. And you can actually go through the, I highly recommend you look at the proof of that, which means you just try to evaluate. So it's very simple. Now that we know that, so that's the sample space, one of which would be the product of the 2 simple multiplication principle. And so probability of one of each is N of one of each over N of S. That's why I think, to me at least, when I'm doing probability, to me it's important to establish my sample space, the size of the sample space first and foremost. It makes life easier. It makes it easier to understand what we are doing. And so the top is simply 6 times 8. The bottom needs to be calculated. Just for the sake of argument, if you need to see the denominator, combination of 14, 2 is 14 factorial over R, which is 2 factorials, N minus R, which is 14 minus 2, or 12 factorials. So I hope you see that the top would be 14 times 13 times 12 factorials. The 12 factorials drop. 14 and 13 divided by 2 factorials. 14 divided by 2 is 7, and you can easily calculate. We're going to go to the next example.
A combination lock consists of the 26 letters of the alphabet. If a 3-letter combination is needed, find the probability that the combination will consist of letters A, B, C in that order. The same letter can be used more than once.
When you make up a password, a code, you understand that ABC again is not the same as BAC. If we were to choose different letters, it becomes a permutation. But it is important, even if this is not given, we should assume there is no restriction because it doesn't mention it. And so what you're looking at really is the total possible outcomes, your sample space. And your sample space, using fundamental theorem of multiplication principle. This is the first choice. There are 26 letters. Here's the second one. There is no restriction. I can use the same letter. Again, 26. The third one, no restrictions. Same number can be used. And that would be the total number of outcomes. Their product, which is simply put equals 26 cubed. If the restriction says the same letters cannot be used, that meaning you can't have AAA. Then what happens if we can't use the same letter? This changes to 25, this changes to 24. So it becomes a 26 times 25 times 24, or the permutation of 26, choose 3, or 26 times 25 times 24, because there are 3 spots. 26 cubed we end up with 17,576 possible. We call it combinations, but it's really a permutation. In other words, 17,576 possibilities. And what would be the probability, therefore? Find the probability that the combination will consist of the letter ABC. There is only one way to get that. So the probability of ABC is n of ABC over n of S. The denominator is given, 17,576. The top, there is only one way, and that's the answer. And this is what I mean by writing a probability as a decimal. It's really not a good idea in a case like this. You probably want to leave it like that. If you were to write it as a decimal, this would become a number very close to zero. So you really have to carry out a lot of decimal. So you can stick with the fractional format or the decimal format. And again, as always, when you do your work online, you follow the instruction.
In a horse race, a trifecta bet is won if we select the horses that finish first and second and third in the correct order. There are 19 horses in a race. How many different trifecta bets are possible?
First, this is the definition of a trifecta is given to us. What we should know that the size n is 19 and r is 3 trifecta. Now we need to figure out whether order is important or not. And because trifecta refers to finding out the proper order of winning the race, it is a permutation of 19 choose 3, n factorial over n minus r factorial, and you take it from there. The denominator is 16 factorial, and for the top we can write 19 times 18 times 17 times 16 factorial. You end up with 5,814. The next one says, what is the probability of winning? There is only one way. There is only one way we can win, 1 out of 5,814 ways. The last part asking, so if that is the case, do all different possible trifectas have the same chance? And the answer is, although there are 5,814 different possible trifecta bets, not all of them have the same chance of winning because some horses tend to be faster than others. Let's look at the next example.
When designing surveys, pollsters sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey with 10 questions, 2 of the questions are identical to each other, and 3 other questions are also identical to each other. For this survey, how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used?
So if you have the same question, but different answers from the same person, that means the person didn't bother to read the questions. And so when they check it, they say, okay, that they may toss it. Here's the way we look at it. And there are 10 subjects, 10 questions, okay, 10 objects, whatever you want to call that. 2 are identical in one case, and in another case, 3 other are identical. And the remaining 5, there are a total of 10, are simply different. So we can use this formula that we have seen before, simply known as, it's a permutation rule, that it is known as distinguishable permutations. So with that being the case, we are looking at the top right formula. So the number at top is 10, and at the bottom we have 2 factorials, we have 3 factorials, and the rest of them are all 1 factorials. Now we're going to write that just because we want to make sure everybody understands. But these parts, we write them because the numbers at the bottom, 2 and 3, and all those ones, they must add up to 10. But all of this, even if you don't write it, the calculation works fine. I just want to make sure everybody understands how this formula works. So normally we write that to tell our readers how things go. And now we just put it into a calculator and we end up with the answer, which is a huge number when you think about it, 302,400 different ways. According to statisticians, for typical surveys, the number of respondents is just about 1,000. Let's go over the next example.
In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39, and the same 5 numbers must be drawn in the lottery. The winning numbers can be drawn in any order, so order does not make a difference. How many different lottery tickets are possible? Find the probability of winning the jackpot when one ticket is purchased.
So understanding the situation, we have the n being 39, r being 5. We are going to deal with 39 numbers, and we're going to choose 5. The winning numbers can be drawn in any order. So order is not important, which means right away we are dealing with a combination. We are dealing with a combination. And so all you have to do, calculate this combination and come up with the answer. So with that being the case, we are looking at combination of 39, choose 5, 39, choose 5, and do the math. 39 factorial over 5 factorial over 39 minus 5 factorial. Okay, now of course, this is 34 factorial. And again, you're not expected to do this by hand, but if you were to do that, you keep the 34 factorial in the denominator, and the top becomes 39 times 38 times 37, 36, 35, and then you stop at 34. So in other words, this one cancels out this one, and it gives us 39 times 38 times 37 times 36 times 35. Okay, so you multiply those numbers, you divide by 5 factorial, or you can write the 5 factorial as 5 times 4 times 3 times 2 times 1. Do the simplification and put the fraction, get rid of basically the denominator and come up with the answer. Now, part B, sadly, the order of the animation wasn't right. So what is the probability of winning is would be very simple. N of winning over N of S. There's only one way to win. Come up with the 5 correct answers. So 1 out of however number we got in part A, in this case is 575,757 different ways. So 1 out of that. That would be the probability of winning. And we are going to move on to the next page.
In the game of blackjack played with one deck, a player is initially dealt 2 different cards from the 52 different cards in the deck. A winning blackjack hand is won by getting one of the 4 aces and one of the 16 other cards worth 10 points, tens and faces. The 2 cards can be in any order. Find the probability of being dealt a blackjack hand. What approximate percentage of hands are winning blackjack hands?
So we are going to write the givens. When you are dealing with a hand, order is not important. You want to get a specific hand that you're interested in. You just want, let's say, an ace and a 10. It doesn't matter 10 comes first or ace. And the definition of a blackjack is given in case we are not familiar with that. So basically an ace and either a face or a 10. Does order matter? We have to. The answer is no, order is not important. So in essence, you're looking at the combination. So what do we have in a deck of cards? We have how many aces? We have 4 of them. Tens, we have 4 of them. How many faces? We have 3 times 4 or 12. So I want to make sure everybody understands how we arrive at these numbers, okay? So again, number of aces is 4. Number of tens is 4. Number of faces, there are 3 faces, 3 types of. So we have Jack, Queen, and King. There are 3 types, 4 suits. We have 12 plus 4, 16. So the number of blackjacks, therefore, would be 4 times 16. There are 4 ways to get aces. There are 16 ways to get tens and faces. So it's 4 times 16. But what is the total number of possible hands? We want 2 out of the 52 cards. So combination of 50, choose 2. Combination of 50, choose 2. Therefore, the probability of blackjack is N of blackjack over N of S. Now again, you can say simply 64 is the numerator. You can say 4 times 16 is the numerator. Or you can say C41 times C16 1. However you want to put that, and the denominator is C52 2. So the top, C4 1 becomes 4. I think I mentioned that. Again, I'm going to repeat that. C and 1 becomes n. So C4 1 is 4, C16 1 is 16, and we've already seen that. Okay, we already have justified the answer of 4 times 16 equals 64. But again, going step by step with the combination. The denominator is 52 factorial over 2 factorial times 52 minus 2 factorial. 2 factorial times 52 minus 2, and that really becomes 50 factorial in essence. Simplification and putting it into a calculator gives us 64 over 1326 or 32 over 663. If you want to put that approximate percentage, is about 4.83%. Now, before we move on, I want to show you actually how to simplify this fraction if you want to do this. So first and foremost, this is 50 factorial. So the top is simply, I'm looking at the bottom, which is 52 factorial over 2 factorial times 50 factorial. You can bring the 2 factorial and the 50 factorial at top. This fraction, again, I'm showing you a complex fraction in case. This one would be 4 times 16 times 2 factorial times 52 minus 2. 50 factorial over, simply put, 52 factorial. See that this can be simplified, and the way you simplify it, this can go away, this can go away and changes to 52 times 51, and now you simplify and you end up with this fraction. This is it. And just quickly, a second method on that, multiplication principle. Probability of getting a blackjack would be the probability of first card being ace and second one be either 10 or a face, or vice versa. Probability that the first one is a 10 or face and second one is an ace. Okay, if you want to go this route. So there are two of them that you want to combine. So the probability that the first card is an ace is 4 out of 52, and the second one is 10 or face is 16 out of 51. When you're looking at this portion, you are looking at this one. Getting an ace, 4 out of 52. Needless to say, it can be simplified. Now, if an ace is gone, then total size of 52 goes down to 51, but the total number of 16 faces and 10s remain intact. So 16 over 51. With the second case, the first card is 10 or face, and the second card is an ace. So this one is the same as the second part, 16 out of 52. Again, it can be simplified times 4 over 51 because they are dependent. Since they are dependent, the sample size shrinks by 1 because one card is drawn.